When we talked about linear growth and nonlinear growth and rates of change, we talked about a situation where you had a cylinder and the relationship between the volume, the radius, and the height of the cylinder. And we did a few problems about nonlinear rates of change in that case. And I wanted to tie that together with our ideas of percentage growth. If we talk about the radius increasing by a certain percentage, how does that change the volume as a percentage? And that problem is, here's an example of a couple problems we can think about along those lines. So we have volume equals pi times the radius squared times the height. That's written down here. The volume is the area of the base times the height. We talked about that. And the area of the base is pi times the radius squared. And so those three variables are connected in lots of different relationships. So let's talk about those for a second. So suppose I fix the radius and all I'm changing is the height and the volume, right? Is the volume a function of the height? And so in that sense, it would be, you tell me what the height is and I have a formula that tells me what the volume is. And if we plug in a particular radius, say in this case it's 5 centimeters, into our volume formula, we can reduce it to a simpler formula that's just the volume is 25 pi times h. So 25 pi is a slope, a rate times the input variable height. And so if I increase the height by 1 centimeter, I increase the volume by 25 pi, in this case cubic centimeters. Another aspect of being linear is if you double the height, to double the input, you double the output, you double the volume. So if instead of h I have, for my height, I have 2 times h, then I can kind of algebraically, I can factor that 2 out and it just becomes 2 times the volume. If I make it twice as tall, twice as volume. So that's a linear scaling, right? A linear function and it's a linear scaling. So how does that happen? What about in the other case? If I have, if I fix the height at 20 inches, and now my relationship is between the radius and the volume. I have a formula for the radius and the volume. If I fix my height, then here's my formula for the volume in terms of just the radius. It's going to be 20, the height, times pi times the radius squared, and radius is still my input. But now the input is squared, so it's not a linear expression anymore. And in this case, if I double the radius, I don't double the volume. I get a 4-fold increase in the volume, right? If I double the radius, I multiply the volume by 2 squared, 4, right? And here's an algebraic way to see that. The intuitive way to see that is I double the radius in the forward direction and also the side-to-side direction. So I've really doubled twice. So I get the area 4 times. Algebraically, I can look at it as instead of the radius, I now have 2 times the radius, but that's squared. So that 2 squared becomes a 4 on the outside, and so I end up with 4 times the volume, right? So that's not a linear relationship, that's a squared relationship. What happens if I do both? What if I change the volume or the radius and the height? What if I double the height and the radius? Well, if you think about my cylinder, I double the height, so that doubles the volume, and I double the radius, so that 2 times 2 to the volume. So I'm going to get an 8-fold increase because it's a 3-dimensional thing. I've changed the width, the length, and the height. So I've really got 2 times 2 times 2 for my volume scaling. Algebraically, you can see that by this pi r squared h. I double the radius, so I get a factor of 2 squared there, and I double the height, so I get a net factor of 2. That's 2 times 2 times 2, or 8. So we can talk about the scaling factors of in these relationships. So what happens if I've got percentage growth or some other, it's not doubling, it's some percent. What if I said I have a small can, say a soup can, and I have a different soup can that's a different radius and a different height? What if I increase the radius by 50%? So that would mean my scaling factor is 1.5. If I increase the radius by 20%, my scaling factor would be 1.2. If I decrease the radius by 10%, my scaling factor would be 1 minus 0.1, 1 minus 10% or 0.9. So I could use those scaling factors with the percentage growth that we've had before. So let's say in this case, my radius increased by 50%, so I multiplied by 1.5. And my height doubled in this case. So my height goes from h to 2h. How does that overall impact the volume? That's the scaling question. I scale it by a certain percentage in the radius, which is actually two directions of length and width of the base, and then I scale by a different amount in the height. Well, here's a way you can look at that. What is the new volume? Well, it's pi times the new radius squared times the new height. And so I can factor out those scaling factors. And what happens is I end up getting the radius scaling factor squared, because it's a two-dimensional thing, and the height scaling factor here times just pi r squared h, the old volume. So I end up getting 1/2 squared is 2.25 times 2 is 4.5 times the old volume. So if you think about it that way, you can look at the scaling factor for different variables in your relationship. If I scale the radius, since it's squared, I have to square that scaling factor. The height is just linear. So if I if I have a scaling factor for the height, I multiply the output, the volume, by that same scaling factor. So you can use that idea to solve lots of problems where, what if I said I end up doubling the volume? How did that change the radius? And I can solve for the scaling factor for the radius, or I change the height and the volume, any of those combinations. This sort of idea lets you figure out the scaling, the relative change of one variable when you know the relative changes of the others. Hopefully that helps a little bit with this idea.